Okay. So those are from other branches. Please see. So it is expected from you that minimum understanding. Okay. You need not to go into the depth knowledge. Then it is expected like you should have basic understanding of mechanical systems, and then if you want to pursue career in IT, no problem. So this is a classic piston cylinder assembly in mechanical engineering. What you see at the outside, this is a cylinder block. What you see here, that is a cylinder head. So outside is called as cylinder. Then inside we have piston, that is a reciprocating part. Then there is a this pin is there or ring is there. It connects piston and connecting rods. What you see here, this is a connecting rod. And here we have crank pin. And what you see here, this is a crankshaft. Okay. So classic assembly. So there is another subject is called theory of machines. So theory of machines, if you is it there in this syllabus? Next semester. Theory of machines, it is actually gives the idea about the mechanisms. So suppose there are two types of joints. So one is a rigid joint. एक rigid support आहे, like bar आहे. So this is a rigid joint. Then there is another joint that is coupled joint. So here this is a rigid joint, and from that we have a coupled joint to another joint. Then there is a three joints are also there. So like this we have rigid support. Then we have one link, then another link. Okay, then another link. Like this way also can be there. So depending on the number of links, their number of pairs, the mechanism is formed. So that will be covered in the theory of machines. So this is actually a 4-bar mechanism, piston cylinder assembly. This link here, what you see is replaced by piston. So here we have a piston, and then there is a cylinder. So piston reciprocates inside the cylinder 2 and 4. This is a crank which rotates. So this is a basic of this piston cylinder assembly, which comes from theory of machines. Then we have this assembly. Okay, so what happens here? Here we have one top dead center, which we call it as a TDC. Okay. Then we have a bottom dead center somewhere here. So piston reciprocates between TDC to BDC. So this is a bottom dead center. Okay. When the piston is at top dead center, wall is closed. As it moves downward, the suction wall is open and then air is inside. Okay. Then it reaches to BDC. After BDC, it goes again in towards TDC. Then discharge wall opens and the compressed air is taken. Okay. So understood? So you are like bar class, like tomorrow we'll go like that. This is a working animation. Air is taken inside, compress and compressed air is taken. This point we are covered in last lecture. Okay. So now first we'll see some of the terminologies which are used in the compressors. First is compression ratio, and very basic, or it is the objective of the compressor, that is compress the air, and compression ratio gives the idea about the pressure ratio. It is defined as the ratio of volume of air before compression to the volume of air after compression. So before coming, let us say maybe volume of air is 1 meter cube, and after compression it becomes 0.5 meter cube. So if you take the ratio 1:0.5, so that will be the compression ratio. Okay, air is compressible and the liquid is incompressible. So that is why there will be compression ratio. Okay, so write down this side by side. It is the ratio of volume before compression to the volume after compression. Okay, next is compressor capacity. The capacity means how much amount of air we can deliver. So it is a quantity of air actually delivered by compressor in meter cube per minute or meter cube per second. So that is the capacity of the compressor, meter cube per minute. Mostly it is given by meter cube per minute. In rare cases they take meter cube per second. Okay, it is the capacity of compressor. एका मिनिटात तुम्ही किती व्हॉल्यूम एअर डिलिव्हर केली, that will be compressor capacity. Next is pre-air delivery or pre-air delivered FAD. So it is the volume of air delivered by compressor under the compressor intake conditions. So हे थोडे understand करायला difficult है the definition. So what is the compressor intake condition? Generally they take it as a 1 bar pressure and 27 degrees Celsius or 300 Kelvin. Generally they take it as a 300 Kelvin. So these are the compressor intake conditions, and at that condition, what is the amount of air delivered? So that is a free air delivery. So actual volume of air delivered, that is a free air delivery. So compressor capacity is quantity of air delivered. So that is theoretical, and free air delivered is the actual quantity of air delivered. Next is swept volume. So might be you all may be knowing this swept volume. So I'll add some slides here. And then we can. Okay. So let us draw piston cylinder assembly. Let us say this is a cylinder block, then inside which there is a piston is there. There is this intake port is there, now exhaust port, or sorry, discharge port is there. So again here, let us say there is this clearance volume is there. This is your TDC. Let us say piston is at PDC, so this is BDC. So it is there in the IC engine syllabus also. So when the volume between TDC to PDC, this is called as swept volume or VS. The small clearance volume which is maintained for the safety purposes. The direct piston down धडकू नये इथं wall आणि damage होऊ नये यासाठी आपण थोडं clearance volume ठेवत असतो. So this volume is called as clearance volume or VC, and total this volume is called as total volume VT. So total volume is equal to VS plus VC. Then there is another term which is called as actual volume. So actual volume delivered, or in our case it is called as FAD, free air delivered. So actual volume is always less than swept volume. Theoretically, this piston cylinder assembly should deliver this amount of air. Okay, theoretically it should intake VS amount of air, compress it and deliver VS amount of air, but actually it does not happen. Actually the actual volume is different. It is always less than VS, and this ratio of VA to VS, it is called as volumetric efficiency. It is called as volumetric efficiency. Okay. So what here we are studying actually swept volume. Okay. So swept volume, I hope you understood. This is a swept volume, the volume between TDC to BDC. Then clearance volume, it is the volume which is kept between cylinder top and TDC. It is maintained for the safety purposes. Swept volume, the volume displaced or swept by piston when it moves from top dead center to bottom dead center. Clearance volume, it is the difference between the total volume and the swept volume. Basically, the gap remains between the piston head and the cylinder head when it is at top dead center. Okay, so next is volumetric efficiency or efficiency. What are the efficiency we are going to calculate? First is volumetric efficiency. Okay, it is the ratio of actual volume of FAD at standard atmospheric conditions in one delivery stroke to the swept volume. Okay, so at standard atmospheric conditions means 1 bar and 300 Kelvin. At that condition, actual air delivered divided by swept volume, that will be the volumetric efficiency. So which I just told you here in this diagram, the actual air to the swept volume, that is your volumetric efficiency. Okay. So write down volumetric efficiency. Now next is isothermal efficiency. So before that, let us understand the PV diagram for the compressor. Okay. Now, if you refer to the diagram you draw yesterday, okay, please refer to that diagram. Now let us draw a PV diagram for the compressor with no clearance value. Okay. Let us say first case is no clearance value. So pressure versus volume. Okay. So let us say piston is here. This is its top dead center. And let us say this is, as there is no clearance volume, let us say this is its bottom dead center. Okay. Sorry. This is again TDC. This is BDC. The piston moves from TDC to BDC. Let us say this is the point 1 where piston is at BDC. Then it compresses the air. Okay. Now there are 3 ways it can compress the air. So it can be isothermally. So if this is point 1, this is point 2. Isothermally means P1 V1 will be equal to P2 V2. Isothermally means the temperature will remain constant. So if I draw a TS diagram, temperature versus entropy. So this is temperature, this is entropy. Okay. And let us say there are 2 pressures we are dealing with. Okay. Let us say this is P1, this is P2. Let us say this is our point 1. Okay. Now, while going from pressure P1 to P2, if the temperature remains constant, so temperature remains constant means this line will be horizontal. So this is the indication that temperature is constant because there is a horizontal line. If the entropy is constant, that will be vertical lines. Okay. So 1 to 2. So this is the isothermal process. Okay. Then 1 to 2 dash, this will be isentropic process. Okay, it can be isentropic also. Isentropic means P1 V1 raised to gamma is equal to P2 V2 raised to gamma. So gamma is a gas constant, and this relation holds good for isentropic processes. Or there can be another process that is polytropic process. Other than these 2, there can be other process that is polytropic. 1 to 2 double dash, or it can be also polytropic. Okay, polytropic means P1 V1 raised to n is equal to P2 V2 raised to n. Okay, so polytropic means any general process. The n is the P1 V1 raised to n is equal to P2 V2 raised to n. If n is 1, then it becomes isothermal process. If n is gamma, it becomes isentropic process. So polytropic means it can be any process. Okay. So there are 3 ways this process can take place: compression, Then there is a 2 to 3. This is a discharge. So at point 2, the discharge wall opens, and this is the amount of air that is being discharged. So this is a discharged air. Now air is fully discharged. Piston is at TDC. Now there is a suction is created, so it reaches to point number 4. The pressure drops. Okay, volume remains same, but pressure drops from P3 to P4 because it needs to create a suction. So at point number 4, the suction valve opens, and outside air is sucked inside the cylinder. So 4 to 1 is a suction. Okay. So 1 to 2, 2 to 3, 3 to 4, and 4 to 1. This is how the PV diagram looks for the reciprocating air compressor. Okay, so you can draw this diagram. So 1 to 2 process can be, I'll write here first, it can be isothermal. That means it P1 V1 will be equal to P2 into V2. Or it can be isentropic. That means P1 V1 raised to gamma will be equal to P2 V2 raised to gamma. Or it can be polytropic. That means P1 V1 raised to n equal to P2 V2 raised to n. Okay. So draw both the diagram PV and TS. Okay. Here this P1 pressure is equal to P4 pressure, and it is called as suction pressure. It is called as suction pressure. Then P2 is equal to P3. It is called as delivery pressure. It is called as delivery pressure. And then this P2 by P1 or P3 by P4, it is called as pressure ratio. It is called as pressure ratio. Okay. Let us move further. Now here we are going to calculate the equation for work. So see the diagram once again. 1 to 2 is what? Compression. Then there are three ways it can happen. Either it can be isothermal. आता बघा isothermal curve आत आहे. So this means it requires less compressor work. Then followed by adiabatic, that is isentropic, reversible isentropic, and then there is a polytropic. So polytropic process requires highest compressor work. So lowest work is required for isothermal work. Then 2 to 3 is delivery of pressurized air. 3 to 4 is suction. 4 to 1 is a suction of outside air. Okay. 3 to 4 मध्ये suction valve open होत नाही. So it has to create sufficient pressure, suction pressure. Then and then only the suction valve will open at 4 and air is taken inside. Again, same case for discharge also. 1 to 2 compress hotana discharge valve open hot nahi. When there is sufficient pressure is created inside the cylinder, then only at point number 2 discharge valve opens and this compressed air is delivered. Okay. So operation, let us see here, 4 to 1 volume V1 of compress of air aspirated into the compressor at P1 and T1. Okay. V1 amount एवढं air त्या cylinder head मध्ये आहे. 1 to 2 air is compressed according to this law. Temperature increases from T1 to T2. So during the compression, temperature increases. Compressed air at P2 and V2 with temperature T2 is delivered. So at this point, this discharge air is delivered. Okay. So now here we want to calculate the work. Okay. Now here in this case, if you take, for example, any process, like let us take a polytropic process. Okay. त्यानंतर आपण बाकीचे process study करू. So let us say there is this polytropic process is there. And this is a compressor diagram. So this is a pressure versus volume. 1 to 2. Let us say compression. 2 to 3 discharge. So there is a 3 to 4 suction. 4 to 1 is a air intake. Now we want to calculate amount of work required to drive this compressor. So this is nothing but this area under this curve. Also, तुम्हाला area दिसतोय. So that is the compressor work. हे आपल्याला derive करायचं. Now how to calculate this area? So there are ways to calculate. So let us say I will show you in simple ways. Okay. So this is the diagram. Once again, see 1 to 2 to 3 to 4. How to calculate this area? Can anybody tell? So first of all, we will calculate area under this curve. 1 to 2. So this will be, let us say this is the area under 1 to 2. Then we'll calculate area under 2 to 3. Let us say this is the area under 2 to 3. Then we'll subtract this much area from the total area. What I'm saying here it is, so we are interested in area 1 to 2 to 3 to 4 to 1. This area is nothing but area 1 to 2, that is area under this curve 1 to 2 plus area under 2 to 3 minus area under 4 to 1. Okay. Now here area under 1 to 2, that is isentropic, polytropic process. So here the formula for 1 to 2, or we'll go to the next slide, then I can explain. For 1 to 2, polytropic process formula is P1 V1 minus P2 V2 divided by N minus 1. 2 to 3 area is simple. This area is nothing but P2 V2, and area of 4 to 1. This is simple P1 V1. So your equation becomes like final P1 V1 minus P2 V2 divided by N minus 1. That is area under 1 to 2 plus P2 V2 minus P1. This way, finally, we are able to calculate this area. Okay. So this way, we will get the compressor work required to drive the compressor. So we'll go to the derivation and then we'll understand. So during the compression, due to the excess temperature above surrounding, the air will exchange the heat to surrounding. Compression index N is always less than gamma, the adiabatic index. As the compressor is work consuming device, every effort is desired to reduce the work. So in isothermal, we require minimum work. So work done is equal to area under PV curve, 1 to 2 dash adiabatic compression. Maximum work is required if the compression is adiabatic. That means entropy remains constant. The medium work is required when the compression is polytropic, that is PV raised to N. And minimum work is required when the compression is isothermal, that is temperature remains constant. Okay, please write down this. This is very important. Work done is equal to area under PV curve, and write down this 1 to 2 dash. So whatever notation you have given, you that one. So तुम्ही आधी adiabatic आधीच्या डायग्राम मध्ये 1 to 2 dash दाखवले असेल तर ते तसं लिहा. त्यांचा आहे असं कॉपी करू नका. Okay, so we'll now derive the equation for the work required for the compressor. Where we are now. Once again, I will show you. So give the title work required. For compressor. सगळ्यात पहिली केस आपण घेतोय for a polytropic process. For polytropic compression. Once again, I will draw the diagram and check. Okay, big diagram I will draw. This is pressure versus volume. Let us say there is no clearance volume. In this way, the diagram will be like this. 1 to 2, 2, 3 to 2. Okay. So 1 to 2 here, what is there? Polytropic compression. That means PV raised to N is equal to constant. 2 to 3 delivery, 3 to 4 suction, 4 to 1 is the air intake. So we are interested in work done, that is the inside area. Okay. So should I change the color? Change the color. Yeah, color. So I will show the required area and the not required area. ठीक है. आपण काय करणार आहे आधी याच्या अंडरचा एरिया घेणार आहे. बरोबर. नंतर आपण याच्या अंडरचा एरिया घेणार. हे झाल्यानंतर आपण काय करणार आहे? We are going to delete this much area. We are going to delete this much area so that remaining this work area will be, we can write. So everybody understood this area? So work, compressor work will be equal to area 1 to 2 to 3 to 4 to 1. This is nothing but area under 1 to 2 plus area under 2 to 3 minus area under 4 to 1. Area under 1 to 2 polytropic compression, that is given by P1 V1 minus P2 V2 divided by n minus 1. Area under 2 to 3 is simply P2 V2 and minus area under 4 to 1 is P1 V1. Write down. Here it is P2 V2 minus P1 V1. Okay, so now I'll take this term P2 V2 minus P1 V1 as a common. So again in this, so you may be asking, sir, exam is online, why we are taking derivation? But it is just an exercise, brain exercise you can consider. So nobody will ask you derivation in multiple choice questions. Okay, it's just an exercise we'll take. Okay, so again WC will be equal to, here I will take P2 V2 minus P1 V1 common. And what will remain inside the bracket? So here it will be 1 upon n minus 1. 1 upon n minus 1 plus 1. Is it correct? So if I take from this term, if I take P1 V1 P2 V2 minus P1 common, it will remain 1 upon n minus 1. From this, if I take common, it will be plain 1. So now calculate this one also. P2 V2 minus P1 V1 inside the bracket. What will be this one? Can anybody tell? Simplification of this. Huh? So how to solve this? Just multiply this into 1. So this will be 1 plus n minus 1 divided by n minus 1. In this case, 1 and this minus 1 will cancel. So this will become P2 V2 minus P1 V1 into bracket n upon n minus 1. Sorry, yes, n upon n minus 1. Correct? Now I will take P1 V1 common. I will take P1 V1 common. So this will be n upon n minus 1 will be there. I'll take P1 V1 common. So what will remain here? P2 V2 divided by P1 V1 minus 1. Okay. So this is a little bit trick is there. If you multiply this again into the bracket, P1 V1 will get cancelled, we'll get P2 V2 and multiply by 1, we'll get P1 V1. So just I have taken P1 V1 outside the bracket, so inside this will be remain. Right? Now see, this process is polytropic. That means P1 V1 raised to n will be equal to P2 V2 raised to n. Okay. Now here I will take V2 V1 on one side, P1 V1 on another side. So here I will take P1 divided by P2 will be equal to V2 raised to n divided by V1 raised to n will be equal to V2 by V1 raised to n. Okay. Message. Okay. Now I will take nth root. Okay, nth root I will take. So it will be V1 by V2 by V1 will be equal to P1 by P2 raised to 1 by n. Nth root I have taken. So square and the square root gets 1/8. So that way I have taken nth root. So that will be V2 by V1 will be equal to P2 by P1 raised to 1 by n. Now I will put this V2 by V1 ratio into this bracket. Okay, into this bracket. So this will become compressor work will be equal to n upon n minus 1 P1 V1 into bracket. We already have what? P2 by P1 raised to what? Correct. So P1 by P2 raised to 1 by n minus. So write down this. So you can simplify this one also. N upon n minus 1 P1 V1 into bracket. So this is 1 minus 1 or 1 by n. So you can write that way also. So it will be P2. You see here, little bit explanation I will give. This is actually P2 into 1 upon P2 raised to 1 by n. So how to write this as 1? This will be P2. Here index is 1. Here index is minus 1 by n. Okay. So whenever there is a rule, so rule is like, let us say there is a raised to a into a raised to b. So ultimately what we write here, a raised to a plus b. Okay, so that's what we write. So that way here index is 1, here index is minus 1 by n. So ultimately it will be 1 minus 1 by n. Okay, or you can write P2 raised to n minus 1 upon n. Okay, so this way we can write P2 by P1, this whole raised to n minus 1 upon n minus 1 bracket. Okay, anybody not understood this? I will explain again. So the rule is any number raised to its index into same, the base should be same. If such multiplication is there, then we can write a raised to a plus b. Okay, this is the rule, mathematical rule. Okay, so here if I take only P2, it is raised to 1 into 1 by P2 raised to 1 minus n. So how we can write this? So we can write P2 as a base. One index was here plus minus 1 by n or 1 minus 1 by n. So this can be written as P2 raised to n minus 1 upon n. So this is the final equation for the compressor work. This is the final equation for the compressor work required. Okay. What is the time? So next I give the title isothermal work. So this was for the polytropic process. Next give the title isothermal work. Okay. So in this case, yes, this is same in every case. The area kasa calculate karaycha, it is same. Only the formula for this 1 to 2 will be different. So as this was polytropic process, formula was V2 P2 minus P1 V1 divided by n minus 1. Now in this case, only the formula will be different. So WC will be equal to, for our isothermal work, this formula is P1 V1 log V1 by V2. Okay, so that only change we have to make here. Okay, so this will be equal to P1 V1 log V1 by V2. Then remaining is same, plus P2 V2 minus P1 V2. Okay, so for isothermal process, P1 V1 is equal to P2 V2, so this will cancel. Okay, and also this ratio V1 by V2, we can write from this as P2 by P1, right? So V1 by V2 will be P2 by P1. P2 by P1 is nothing but pressure ratio, or small r we can write. So finally, what will the compression equation? So P2 V2, these two terms will get cancelled because these are equal. Here only thing will remain is P1 V1 log P2 by P1. V1 by V2 is nothing but P1 P2 by P1, or we can write that P1 V1 log R. Okay. Again, from ideal gas equation, P1 V1 we can write it as a MR T1, correct? Ideal gas equation, PV is equal to MRT, and finally we can write down isothermal work as MR T1 log R. Okay. So this is the isothermal work done. And the last case is isentropic compression. So that also I have. Third case is adiabatic, or you can write reversible isentropic. Okay? Isentropic compression. Isentropic is nothing but reversibly adiabatic. Okay, reversibly adiabatic. So in this case, what is the equation? P1 V1 raised to gamma is equal to P2 V2 raised to gamma. Here gamma is nothing but gas ratio. Okay, is the ratio of Cp divided by Cv. So Cp is specific heat at constant pressure. Cv is specific heat at constant volume. It is the ratio of Cp by Cv. So what is the relation? Compressor work we have calculated n upon n minus 1, correct? Into P1 V1 into bracket P2 by P1 raised to what? N minus 1 upon N or minus 1. So this equation already we have derived. In this case, just replace N by gamma. So for isentropic, compressor work will be equal to gamma upon gamma minus 1 P1 V1 into in bracket P2 by P1 raised to gamma minus 1 upon gamma whole minus 1. This is the equation for isentropic process. If the 1 to 2 is a isentropic compression, then the work is or compressor work is given by this. Okay, so these are the three cases. I hope you understood. So we started with the polytropic process, then we went for isothermal, MRT1 log R, and this is the last isentropic. Okay, another formula is there for this isentropic. So here this WC is written as mass MCP T2 minus T1. This is also for isentropic process. Okay. So this formula you can use when you know pressure values, and this formula you can use when you know temperature values. Now we'll take one numerical so that you will understand. Okay, so write down a single stage reciprocating air compressor. The reciprocating air compressor एवढं लांब लेज असलेल्या किंवा शॉर्ट मध्ये RAC लिहा कॅपिटल. So single stage reciprocating air compressor takes 1 meter cube of air per minute. Takes 1 meter cube of air per minute at 1013 bar. At 1013 bar and 15 degrees Celsius. And delivers at 7 bar. And delivers at 7 bar. Assuming PV raised to 1.35. Assuming V's index is 1.35. PV raised to 1.35 is equal to constant and no clearance volume. And no clearance volume. Calculate indicated power. Calculate indicated power. Indicated power means this compressor work. So this is a term as indicated power. Indicated power. So can you calculate all the values are given in this problem? N is given. N is how much? 1.35 is given, right? In that problem. Pressure is given 1.013, volume flow rate is given 1 divided by 60 or 1 meter cube per minute. Pressure values both are given, N is given. So calculate, all the values are given, calculate the compressor work or indicated power. So calculate it. How much power you got? So say equation was n upon n minus 1 into P1 V1 into in bracket P2 by P1 raised to n minus 1 upon n minus 1. So put the values. What is n? 1.35 divided by 1.35 minus 1 into P1 kitila hai 1.135 was 013, right? This is in bar, converted into Pascal, that is 10 into 10 raised to 5 into volume flow rate is given 1 meter cube per minute. We will convert this into meter cube per second, 1 divided by 60. Now in bracket P2 by P1. P2 is how much? 7 bar divided by 1.013 bar. Now you can convert this into Pascal, but ultimately the 10 raised to 5 will be cancelled on both sides. So no need to write here, or you can write if you want, if there is a confusion. So this raised to what? 1.35 minus 1 divided by 1.35 and whole minus 1 and bracket complete. So in your case, say in single stage you can solve this. Just you have to properly put the values. One stroke मध्ये तुम्ही solve करू शकता calcium मध्ये. One 147. No, no, it's okay. It's okay. What is the unit? Watt. Your answer is different. What is the answer? Sudhir, how much? In one stroke you can calculate. Just synthetic air. So maybe some brackets here and there. You can. I remember. How much? Where is your calcium? When I say you need basic understanding, doesn't mean you don't need calcium. At least you should have calcium. What about yours? Room मध्ये. At least you download the app on Play Store. Go to Play Store. There is the app Calculus. This is correct. No. Are same calcium there. Why everyone is showing different results? Ask me, how much you got? Same means what? Same of what? Last page there. How much? Okay. Fats. Okay. Okay, what? How much? Those are in online mode. Please also reply. 4 point. 10 raised to. So this will be watt, or you can write down 4.23 kilowatt. No problem. This is your indicated power, 4.23. Shall we take one more problem? What is the time? Okay. We'll go to the next point, last point today. That is volumetric efficiency, because our next problem requires understanding of this derivation. Okay. So I think we have derived up to this point, right? So yes, in book you may observe this formula. Okay, n upon n minus 1 m r p1, 1 minus. In our case, we have derived p2 by p1 and then minus. So then, because the work is negative, so we have already assumed that work is negative. If you calculate by this formula, you will get negative value. If you calculate by our formula, you will get positive value. So don't get confused. In book, you may find this formula in some books. So what I referred from this Rajput book, our formula is similar to Rajput book. So our formula will always give you positive work. That means that is a compressor work. This formula will give you negative work. So negative work means because it is a compressor work, work is done on the system. So that is why it becomes negative. The solution of this equation is always negative because it is a compressor work. Now next is clearance volume. So volume that remains inside the cylinder after the piston reaches the end of its inward stroke. There are many reasons to keep clearance volume. Majority or a major reason is for the safety reasons. The piston's head do not come in direct contact with cylinder head. For that purpose, we are keeping clearance volume. Now here the equation is what is the effect of clearance volume. This case आपण जे बघितली त्यात clearance volume नव्हता. Now this case is with clearance volume and this is its PV diagram. So watch carefully. So here is the point 1, piston is at BDC. Now it moves upwards, compresses the air, it moves to point number 2. Point number 2, discharge valve opens. 2 to 3 is a discharge of compressed air. 3 to 4 is again suction. At point number 4, the suction valve opens, and 4 to 1 is a air intake. Okay, so in this case, this is the clearance volume. What you see here, this much is the clearance volume. This is where piston is at BDC. This is where piston is at TDC. And this is the clearance volume. Okay. Now, what is swept volume between TDC and BDC? So this much is the swept volume. Correct? And effective swept volume that is given by V1 minus V4. Yes, so this is a effective swept volume. Total volume will be this much from V1 to 0. Okay. So draw this diagram. Reciprocating compressor with clearance volume. Now here the question arises that, sir, what is the effect of clearance volume? The मागच्या केस मध्ये आपण derivation केलं without clearance volume. आता clearance volume आलाय. What will be the effect on indicated power? The power वर काय फरक पडेल का? So the answer is no. Okay, so this may be your MCQ question. The effect of clearance volume on indicated power, it is 0, or there is no effect of clearance volume on indicated power. So there is a big derivation is there. We'll see. No need to derive once again. We'll just go to the conclusion. So who will tell me what will the work, indicated power in this case? What will the area? So answer is there actually on the screen. Indicated power will be 1 to 2, 2 to 3 to 4 to 1. So I will draw by another color so that you will understand. So this area under this cycle, this is our indicated power. Okay. How to calculate this indicated power? First to calculate this area. 5 to 1 to 2 to 6. You calculate this big area. Okay. So calculate this big area 5 to 1 to 2 to 6 to 5 minus 5 to 4 to 3 to 6. So the area which has to be deleted, I will ink with another color. So from this green area, we have to delete this orange area 5 to 4 to 3 to 6 to 5. So that remaining area will be this one. Okay. So no need to show hash line. I was just showing for the understanding purpose. Now see what is the effect of clearance volume on indicated power. So when you consider clearance volume, the final equation is same as that of without clearance volume. So that way it is said that there is no effect of clearance volume or VC on indicated power. Okay, so this may be your MCQ examination. So write down just one sentence. There is no effect of clearance volume on indicated power. Okay, I think this is sufficient for today. Next lecture. Huh? No need to write because it will be, I'll give you in the ISC, that way you can check. You can refer to the books. Okay. So in next lecture, we'll go for this derivation of volumetric efficiency. Then there is one problem is also there, and then we'll see actual PV diagram. Okay. These 2 points will be covered in next lecture. In upcoming lectures, after that we'll go for multi-stage compression. There is a derivation for multi-stage compression. We'll do that and then do some numerical. So I think 3 more lectures will be required to complete this chapter. Today is 12, and I hope up to 15 I will be able to complete this chapter. Then up to 20 we'll cover the syllabus. Like that way, maximum 20 we can do. Okay. Any doubt up to this point? I will just take a recap whatever we have done today so that you will not forget afterwards. We started with definitions of compressor. Then we went towards the PV diagram and TS diagram of reciprocating air compressor. The compression can be achieved by 3 processes, either isothermal or isentropic or polytropic. Then we started with polytropic power. Okay, so this was the derivation we did for the polytropic compression. Final equation was like this: n upon n minus 1 into P1 U1 in bracket P2 minus P1 bracket raised to n minus 1 upon n minus 1 bracket complete. So this way equation was there. Then we derived for the isothermal compression. In that case, we get the equation MRT1 log pressure ratio. And finally, we went for isentropic compression. So that way, in each case, we calculated indicated power. Then we solved one numerical based on it, calculated the indicated power. Simple numericals will be there. And next lecture, we'll take advanced numerical. Next lecture, we'll go for volumetric efficiency, actual work, and some more numericals so that you will understand. Okay. So those are in online mode. Put your attendance in the chat box.